Okay, so today we're going to talk about the explicit equation for geometric sequences, and we're going to get into the form of this, and we're going to do this with some zombie problems here. But we're going to start with problem number 1 here. We have one person is infected in your class and turned into a zombie during your assessment yesterday. And each day after that, 2 more of your classmates got infected. 2 more of the class, so 2 more people in your class got infected each day after that. So when we do this problem here, what we're going to do is we're going to kind of think here. So the first day, we have 1 zombie. So there I have 1 zombie on my screen right now. Okay? So on day, so you kind of think about that, that'd be like our kind of day 0 here. I'm going to put that in here in our table. Generally it wouldn't show up, we know, for sequences and stuff like that, but day 0, okay, we have 1 zombie. That's our like starting amount we have, because you can't have the disease really start without having somebody start it. Okay? So then let's think here. Now on day 1, all right, how many zombies would be there after day 1? Okay, well, it says each day there are 2 more infected. So what I'm going to do is I'm going to infect 2 more people. So let's infect a couple more people here. I got 1 and I got 2 more. Okay, so I got 2 more zombies on there. Then that's all it says, is just 2 more people got infected. So think about that. How many zombies are now there after day 1? Well, we have 3. Okay, so then this is going to keep happening again. Okay, now on day 2, think about how many zombies you'll have. Okay. What I want you to do now is I want you to pause the video and I want you to try and finish the table. Okay, now resuming the video here. Okay, now that you have this table done, on day 2 you should have 5 zombies. You should have 5 zombies. You should have infected 2 more people, okay, in the class, which gives you a total of 5 zombies. Okay, and this pattern is going to keep going. On day 3, we would infect 2 more people. We would have 7 zombies. Then day 4, we would have 9 zombies. Okay? So what I want you to do right now is I want you to write the explicit equation for this pattern here. I want you to write the explicit equation for this pattern, so go ahead and pause the video and do that. Okay, now resuming the video. Okay, you should have written for your equation. You should have noticed this is an arithmetic sequence. You're adding 2 zombies each day. Adding 2 zombies each day, no matter what, that's all that's happening. So we should have it in the y equals mx plus b form, or our slope-intercept form. So I'm going to have t of n equals. Our growth here, or our common difference, that growth is 2, and it's a positive 2, so I'm going to say 2n, okay, because we're using n and t of n. And then our 0 term, the amount, that's like the starting amount. Our starting amount here is we needed 1 zombie to get started. So the equation for this pattern is t of n equals 2n plus 1. Okay, so this one followed an arithmetic sequence. Now, not every pattern here is going to follow an arithmetic sequence, so we're not going to have the same form of t of n equals 2n plus 1, or that y equals mx plus b form, that slope-intercept form here. So let's go into problem number 2 here. And this one we'll walk through together. One person in your class has been infected and turned into a zombie yesterday. They came to school today and infected 2 more of their classmates. Each day after that, each zombie comes back to school to infect 2 more of their classmates. So they get to keep infecting here. They don't just infect him one time, they infect him every day after they turn into a zombie. So let's go ahead and let's make a little table here to help out with this, okay? So we're going to run with n, which is our days. Again, we'll make n our days, and we'll make t of n our number of zombies, okay? That's what we're going to use here. So thinking here again, on day 0, okay, we'll just put day 0 in here just for this case, okay? For day 0, I know it won't show up in an actual sequence, but we need it here. For day 0, how many zombies do we have? We have 1. Okay, that's the starting amount that we have in this case. We have 1 zombie. And it says each day they infect 2 people. So he comes back to school and infects 2 people. So I'm going to infect 2 more people. Okay, so on day 1, he's already infected these 2 people. Okay, so you can kind of think here. Day 1, he's gone to boom, and boom, he's infected these 2. So on day 1, we have how many total zombies? Well, in this case, we have 3 zombies on my screen. We'd have 3 total zombies. Now on day 2, okay, the next day they come to school. They each, so all 3 of them are going to infect 2 more people. Even the person that's already infected 2 people the first day is going to do it again. It's going to be a little bit different than the other one. They're going to infect, each of them are going to infect 2 more. So I'm going to go ahead and I'm going to put 2 zombies for each of them. So I'm going to say here's another 2 for the guy up top, for the first guy that we had. The guy down here that got infected on day 1. We're going to put 2 with him. Then we're going to put 2 more with that one. Okay, so now that we have that done, we now can see on day 2, they've each infected 2 there, 2 there, and he went and infected 2 more again. So think on day 2, how many zombies do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 8, 9. Now, we can continue to do this again, okay? But I want you to see if you notice a pattern with your table now. Instead of me having to add all these zombies, I want you to pause your video and see if you can notice a pattern in the table. All right, now resuming this, you should notice here, from 1 to 3 and then 3 to 9, that's not constant addition. In this case, it would be timesing by 3. Timesing by 3. So that's our pattern here. That's our geometric sequence. Okay, so we could go say day 3 has 27. Day 4 has, that would be 91. 81. And so on and so forth. So when we think about this, we could think, well, how did we get the pattern here? Well, to get 1, we just had 1. To get 3, we did 1 times 3. To get 9, we did our starting amount 1 times 3 times 3. We multiplied by 3 twice. To get 27, we would have to multiply by 3 again. So we'd have to do 1 times 3 times 3 times 3. To get 81 would be 1 times 3 times 3 times 3 times 3. You'd have to multiply by 3 4 times to go from the starting amount to get there, and so on and so forth. So think about what is repetitive multiplication here. So think back to what we studied earlier this year. Repetitive multiplication is exponents. I could shorten this up. There's 3 4s here. So I could say this then is 1 times 3 to the 4th power. For this one, for the one above it, it'd be 1 times, how many 3s are? 3 to the 3rd power. For day 2, it would be 1 times 3 to the 2nd power. For day 1, it would be 1 times 3 to the 1st power. And think here, for day 0, how many times do you multiply by 3? Well, that's none. So that'd be 1 times 3 to the 0 power. Well, hopefully you're noticing a little connection here. N is the number of days. That's our exponent for each of these. That's telling us how many times we need to multiply by 3. So if I put an n here, I then have for n days, well, that would then, in this case, be 1 times 3 to the nth power. And that would give me the number of zombies. Okay? So we have a pattern there. Hey, there's kind of a little equation there. Okay? So let's keep that in mind. Let's look at one more here. I'm going to leave that table on here. For this one, we start with 2 zombies, and each day they infect 3 people. Okay, so I'm going to make a table again. We have 2 zombies, so we have our days, which is our n, and our t of n, which is number of zombies again. Day 0, we start with 2 zombies. So I guess I could put 2 zombies on my screen here. There are 2 zombies now on the screen. Each day they infect 3. So I'm going to put 3 for each of these. This is going to be a little tough, so I have 1, 2, 3. I'm going to put 3 more. 1, 2, 2, and 3. Oops. 3. So there's our 3 zombies for each of these. Okay, so they're kind of overlapping, but he infected 1, 2, and 3. 1, 2, and 3. Okay, so think on day 1, how many zombies do we have? Well, we have 8 zombies. Okay, now each day after that, they're going to continue to infect 3. So all 4 of these people are going to infect 3 more. All 4 of these people are each going to infect 3. So you can kind of think there's 3 more off of each of these. Well, that would make 3, 6, 9, 12, 14, 16, or 4, sorry, 3, 6, 9, 12, 15, 18, 21, 24. But you also need to count, these people are still zombies here. So that would also give us another 8, which gives us 32 total zombies on day 2. Okay, you can kind of draw it out with a little tree, but it gets harder as you infect each of them with more. Okay, now there's another pattern here again. Okay, you can see in this one, this time it's timesing by 4 to get to each of these. So if I wanted day 3, I would times by 4 again, and I would get 128, and so on and so forth. So looking at this again here, to get 8, we did 2 times 4. To get 32, we did 2 times 4, but we did it twice, times 4. To get 128, we did 2 times 4 times 4 times 4. Well, that same pattern holds true here. Okay, that one's just 2 there. For 2 times 4, for day 1, that is just 2 times 4 to the 1st power. We only multiply by 4 once. For day 2, it is 2 times 4 to the second power. For day 3, it is 2 times 4 to the third power, and so on and so forth. For day 0, it would be 2 times 4 to the 0 power. So for n, we could then say it is 2 times 4 to the nth power. N tells us how many times we need to multiply by 4. Okay, so that is our pattern here. Now you'll notice they're both the same. The 2 here, that's how many we have on day 0. The 1 was how many we had on day 0. The 4 is our common multiplier. That's what our growth pattern is. That's what we're growing by. And same with the 3 on the other one. So that gives us the C. That's how the equation is always going to work for exponential. So I'm going to go ahead and I'm going to write that up here. So the general form for an exponential equation is, for a geometric sequence is T of n equals B times G to the x, B times G to the n, where B is our starting value, that's our T of 0, and our G is our growth, which in this case, for geometric, we like to call that our common multiplier. Okay, our common multiplier. And then for n, that's just going to be that's our term number. Okay, so that stays our term number, and our T of n is our term. Okay, our T of n is our term. So you still have to do the same thing. You still need to find your growth, or the sequence generator, which in this case for geometric sequences is your common multiplier. You got to find your 0 term still, but it's in this form where we have exponents. That's where we get this exponential idea. So I'm going to do an example here on A. Okay, I have a sequence here. I have 5, 15, 45. Okay, so I'm going to find that I'm going to look for that sequence generator. And in this case, I know from 5 to 15 is adding 10, but adding 10 doesn't get me to 45. So in this case, you got to think multiplication. That's multiply by 3. Multiply by 3 to get to the next one. So in that case, that is my G. That is my growth. So I'm going to put that in the growth part. So that would be I'm going to label it here. My G here is timesing by 3. But I need to find that B value, my starting value. Well, that's our 0 term. So remember, to get the 0 term, you need to go backwards. So instead of multiplying by 3, I'm going to divide by 3. Okay, 5 divided by 3, oh, that's an ugly decimal. So I'm going to leave that as 5/3, just 5 over 3. That's 5 divided by 3. So that's my B value here, 5 divided by 3. So the explicit equation for the sequence then is going to be T of n equals our 0 term, which is 5/3, times our growth, and in this case we're timesing by 3. I'm going to put in parentheses, times by 3, but we don't know how many times we're going to multiply by 3, so I'm going to put the n on the outside of the parentheses because that's going to be my nth term. So if I wanted to find the 100th term, I could put 100 in for n, and you'd have to use exponents here. Instead of just multiplication, it is exponents for the nth power. So I'm going to put up another one here, B. B here, I'll give you 14, 28, 56, and so on. What I want you to do is I want you to pause the video and I want you to try and write this explicit equation for this sequence now. All right, so resuming the video here now, you should have found that the growth was times 2. That's what you're doing each time. You're multiplying by 2 each time. Then you need to find the 0 term. So to find the 0 term, work backwards. Instead of multiply by 2 to work backwards, you have to divide by 2. So 14 divided by 2 is 7. Okay, so I have T of n equals our starting value, which we found was 7. That's that 0 term. And we're going to multiply that times our growth, which is 2. So I'm going to say times by 2 to the power of, we don't know how many times we're going to multiply 2, so then it goes to the power of n. Because remember, the exponent represents repetitive multiplication. All right, so I'm going to give you one more here, C. I'm going to give you a table here of 0, 1/2, 1, 2, 2, 8, 3, and 32. I want you to pause the video and try and find the equation for this sequence. All right, so resuming the video here. Okay, so this one's a little tougher. If you can't see the pattern right away, what you can do is take a term. I see an 8, and divide by the one that comes before it, divided by 2. 8 divided by 2 is timesing by 4, so that'd be 4. So check, 8 times 4, does that get you 32? Yes. Does 1/2 times 4 get you 2? And that is yes. Okay, and they already give our 0 term. So we're going to write the explicit equation here as T of n equals, our starting value is 1/2, and then times our growth, which is 4. We don't know how many times we're going to multiply by 4, so that is to the nth power. And that would be the explicit equation here. If you have any questions, please let me know, and we'll continue this as we progress through the unit.